All right, folks. Well, welcome back. Hopefully, you're able to get the work done yesterday. Watched the video yesterday. Hopefully, that cleared up some things for you. What we will start today then is, or what we will continue today is our discussion of acceleration and what that means. I'll review that with you in just a moment, but please make sure you check Classroom. I have posted for you like I pointed out to you, I put together a packet for you already for you to do in order to practice the work that we've done so far. So if you look on Classroom, you'll see there then that I have posted for you the first set of practice problems that you can do. The practice problems there will help you to help reinforce, hopefully, for you the discussion we had on position time graphs and how we can interpret the position time graphs and what they mean for us. Please make sure that you are able to interpret those graphs, be able to obtain the information from them, but also be able to look at what it says and be able to interpret them in terms of how an object moves in a straight line manner as well. So work on those problems. I've assigned it for tonight, and it will be due tomorrow. But do the best you can with it. When we get back from break, I will take questions on it. Come by on that first day after school. I'll try to work out a couple problems for you from that packet, and I will post a second packet for you as well, hopefully this afternoon, if not tomorrow, and which I will assign to you when you get back from break. Okay, so please make sure you practice that. And if you have any questions on how to do these problems, make sure you come by and see me. Okay, that second packet will involve you calculating for velocity using the equation that we were able to derive for velocity from the position time graphs. And make sure you're able to understand then that when we graph, the whole idea behind graphing information, graphing data, is that we can try to see patterns in the data. Okay? And once we can see patterns in the data, if we can establish an equation, that is even better, because what happens then is that equation becomes predictive. Now, we can use a graph also to predict. We can extrapolate or interpolate within a graph, and those are two skills that you'll learn when you take physics or when you go on to higher math. For those of you who already are taking physics or have learned about it, we can make predictions from a graph as well. But it's a little bit easier if we have a formula in order to make those predictions. And so we can solve for the unknown and use that to make a prediction as what will happen. And that's the power behind having these formulas. And so what we're going to do then is I'm going to introduce to you, as you see on the screen today, then the second formula that we're going to use. So we already know how we can calculate for velocity and what the velocity's relationship is to displacement and time. Today, then, I'm going to introduce to you a second equation that will define for us acceleration. And then what we're going to do is we're going to take a look at the graph that will give us this particular equation here. Okay, so we're going to kind of do things a little bit backwards here, but that's what we're going to do. Okay, all right. So how did we define acceleration yesterday? Okay, yesterday, I introduced to you this idea of acceleration as being a process, as being a description of how an object moves, and that description that we consider, that we define then as acceleration, is basically the change in speed that an object undergoes. If an object undergoes a change in speed, it accelerates. So the acceleration then is defined then as an object either speeding up or slowing down. So you got to make sure you keep this in mind then, that when we talk about acceleration, and this is something that a lot of folks are not clear about, we are talking about a change in speed, which means then the object is speeding up and slowing down. So the example that I gave you of the race car, when the race car takes a corner, it's going to slow down. Then when it takes another corner, it speeds up. So the process of speeding up and slowing down, so the change in speed, and that's what you got to make sure you understand, and the acceleration defines a change in speed, then we have an acceleration. However, in terms of physics then, an object that also changes its direction. So an object that changes its direction also undergoes an acceleration. And when we talked a little bit about this when we discussed Newton's second law in the first semester. Newton's second law related for us the relationship between force, remember force is push or pull, and the acceleration. So an object can change, it can accelerate if it moves in a circular manner. We talked about that. That torque that we talked about, that's the force applied to an object in order to get it to spin. And as that object changes its direction, it undergoes an acceleration as well. Okay, so make sure you keep in mind then that acceleration indicates both the change in speed and a change in direction. Now, we've talked about the change in direction already. What we're going to focus in on here is we're going to focus in on how we can calculate for the change in speed. Okay? And so if you take a look at the equation here that's given to you, it relates then, acceleration then is going to be a, and if you notice there's that bar on top, which means then acceleration is a vector quantity. Okay? So it's a vector quantity because it's defined then as a change in speed with a given direction. Okay? And if we're defining it as a change in speed or change in velocity, then if you notice here, then that would be then the final velocity minus the initial velocity, the difference between the two. And understand this, these velocities here that are described here, these are instantaneous velocities. We talked about this in the last unit, okay, I'm sorry, in the last part of this discussion. This is the instantaneous velocity or the velocity at a given time, okay? So this is the velocity at time final, and this is the velocity at time initial, okay? And so remember we talked about what these instantaneous velocities, that's probably spelled wrong. Anyhow, what this instantaneous velocity is. It's a speed at a given moment in time. We can calculate for that using limits on the time interval there, or we can calculate for it by using a line that is tangent, by using a position time graph and finding a line tangent to a given point and calculate for the slope of that line. We get then the instantaneous velocity as well. You do not have to calculate for the instantaneous velocity in this particular section here. You just need to know then what the velocity is at a given moment in time. Okay, so we're dealing with instantaneous velocities in this particular description of acceleration. Okay? And so that's how we can describe acceleration: change in speed, change in direction. We can calculate for that change in speed. We can calculate for that acceleration if we know the two velocities. We know two velocities: velocity at a time that we call time final, and a velocity at a time that we call time initial. Okay, and if you notice then, if we do the quick unit analysis, and I won't do this for you, but if we do a quick unit analysis, the units for velocity then is going to be units of meters per second squared or length over time squared. Okay, so those will be the dimensions of acceleration. Okay. All right, so with that said then, this is just to quickly clarify for you then what we will be doing with velocities here. So we have a car moving. The velocity here is the velocity at this moment in time that we call time initial. At the initial moment, it starts to speed up. It starts to speed up, and then at some time final, it's going to be at a different speed, a different velocity. So we have two different velocities that we can calculate for, okay? And so therefore, the fact that it changes its speed, we have then a change, we have an acceleration. We're not going to deal with change in direction here, folks. So we're only going to look to define then whether an object accelerates or not. We're going to see then if the object changes its velocity. Okay? And so we're going to use these two velocities here in order to calculate for the acceleration. And if you notice again, we are defining these two accelerations these two velocities as the velocities at a given moment in time, and thus we're dealing with instantaneous velocities. Okay. All right. So the acceleration then is a vector quantity, like I said, because objects will accelerate in a given direction, right? And so this is going to be key here, folks, and I want to highlight this for you. Okay. The sign of the velocity, okay, and the sign of the acceleration, okay, does designate whether it's going to speed up or slow down. Okay. We can look at the signs and determine then whether they will speed up or slow down if they are the same. So let's go ahead and I'm going to make sure everyone understands this. Okay, when the directions and the signs are the same, then the speed increases. Okay, so the object is speeding up. Okay, when the signs are opposite, when the velocities are opposite, the velocity and the acceleration are opposite in direction, then the object is slowing down. Okay, so in this first case, then the object is going to be speeding up, which means then the acceleration and the velocities have the same sign. That means both are either positive, both are negative, doesn't matter, okay? But positive or negative, they have to be in the same direction, same sign. That means the object is speeding up, okay? So the object is speeding up, okay? And so in the second case, then the object is slowing down. And when that's the case, okay, the sign for the acceleration and velocity will have opposite signs. Okay, one will be negative, one will be positive, but their signs are opposite. Here the signs are the same. When the object is speeding up, when the object is slowing down, these two vectors will have opposite directions. Okay, so you want to make sure you keep that in mind as we move forward with this. Okay. All right. So let's go ahead then. Let's look at an example problem here, and I want to work out this problem for you. Okay. What is helpful here, folks, and what I would suggest you do is with all these problems that we do, what we'll do here together in discussion, what you'll do when I have that packet for you, when you solve these problems for acceleration, you have to draw the pictures. Okay, so take a look at this here, and hopefully you have it on your own slide there. Okay, so I'm gonna I'm gonna clear the screen out for me so I can write this for you. Okay, all right. So well, let's go and consider what we have here. Okay. Let's write down what we have first, okay, and indicate what we have first. So again, make sure you draw the picture, and that's what I'll do for you. Okay, so we have an object. The ball here is our object, okay, and it starts to move, okay, and it rolls up a driveway. So we push it up a driveway at this rate here. Hopefully everyone sees then that is your speed. The direction will be indicated in just a moment. So therefore, this also represents a velocity. Because remember, speed is just the magnitude, how fast an object is moving. Velocity is how fast it's moving with direction. So right now, all we have is how fast. So we have our speed here. Okay. We're told then that it rolls up the driveway for a time interval of 5 seconds. Okay. And then it stops. This is going to be key here because we'll talk about this. It'll stop. Okay, we'll talk about this in just a moment. And then it rolls back down. We're told then the positive direction is up the driveway. Okay, and the origin is at the place where the motion begins. So we'll indicate all that. It's indicating for us where we should designate the origin. Okay, and so the question is, what is the sign and the magnitude, okay, of the acceleration? So how do we know that this object accelerates? Now remember, acceleration is defined, and we did this, as the change in velocity over the change in time. Does this object change its velocity? And the answer is yes, because this is where it starts out, okay, and we'll show the sign in just a moment, but this is what it's starting with, so that's the initial right there. What do you think the final velocity is going to be? Well, in the description here, it tells us that the object stops. Okay? When an object stops, and that will be your final velocity, what is its velocity? 0. And so therefore, this ball here does have an acceleration because it changes its velocity. Now, we know that it slows down, and from common experience, we know that it slows down. And so based on the previous slide, and hopefully you made note of that, we expect then that the sign for the acceleration and the sign for the velocities to be different. They should be different. They should be opposite, and that's how we know that it's going to slow down. And when we do the calculation, you will see then that the signs will be opposite. Okay, so let's go ahead then, and I'm going to go ahead and I'm going to I'm going to make a screen here for me so I can work this out for you. So the first step you should do, and this is something you should always get in the habit of doing, especially, and I know all of you folks, since you're going to be, you're interested in engineering, you should always draw this, especially when you get into physics, because almost all of you will, okay? You should always draw the picture. Okay, so let's go ahead and draw a picture. There is our inclined plane. And folks, for those of you who've done inclined planes before, you know how painful it is to do these problems without the picture, okay? Okay, so there's our inclined plane. There's the ramp, okay? Here is the ball down at the bottom of the ramp, mass M. We don't need to know that now, okay? We are told then that the origin is here. So this is going to be, X is going to be equal to 0 at that point, 0 meters. This is our origin. We are told then that up the ramp is positive direction, down the ramp is the negative direction. Okay, so there's our positive and our negative. And we're told then that the ball moves up the ramp and it moves with an initial velocity, and let's go ahead and write this down. It moves with an initial velocity, okay, because the direction is up, initial velocity of 2.50 meters per second. Okay, so that's initial velocity. Now, we don't know how far up it goes, but we know the time interval. So therefore, the total time interval, T final, that means minus T initial, the time interval here is going to be 5 seconds. Okay, that's our time interval. At the end of this time interval, I'm just going to draw this as a dash liner. We know that the ball ends up at some position up the ramp, At the end of this time interval, the ball stops, which means then V final then is going to be 0 meters per second. Okay, so that's what we know so far about how this object moves, about how this ball moves. And I've indicated all that in a very simple drawing. So get into the habit of doing this, folks. Draw the picture, okay? And then what you want to do next is you're going to write down the formula that we need to solve this, because they're asking us about the acceleration. So therefore, the formula for acceleration then is going to be the change in velocity over the change in time, okay? And so with that said then, just to substitute in here what we have, change in velocity is going to be V final, the velocity at time final minus velocity at time initial, okay? Okay, T final is T final minus T initial, okay? All right, so with that said then, we're going to substitute in our values that we have here. If the time interval here is 5 seconds, then, okay, so T initial then is going to be 0 seconds. T final here then is going to be 5 seconds. Okay? And so that's why typically, unless they indicate what the initial time and the final time is, if they give you a time, it's always going to refer to it as a time interval. That's why then this bottom, the denominator, you really don't have to do. You just have to make sure you plug in this time interval here for delta t here. Okay. All right. So let's go ahead and plug it in. Let's plug in what we have. Okay. We have then V final. V final here is going to be 0 meters per second. Okay. V initial here is given to us as negative 2.50 meters per second. The time interval then is going to be 5 seconds. And so the equation here is already set up for us to solve for acceleration. We don't have to rearrange the equation. The formula that we use for acceleration will be the equation that we'll use to solve for the problem, so we don't have to rearrange it. So plugging in our values then, you're going to see that the value for acceleration is going to be negative because of this, and the value then is going to be negative 0.500. And if you notice then, the units then will be meters over seconds, which is going to be meters per second squared. And like we said, the dimensions for acceleration, length over time squared. Okay, so that is the acceleration. Okay, that's your acceleration. Now the question is, how do we know that this object is slowing down from the numbers that we were given? We know that the object, the ball, will slow down based on our common experience. We know then that as any object rolls up a hill, at some point it's going to stop because gravity is going to pull it back down. Okay? The acceleration here, folks, make sure you keep this in mind. Velocity is up, the acceleration is down. Why? Because acceleration is in the negative direction. So if you notice here, velocity here and the acceleration here are in opposite directions. Okay. And so because it's in opposite direction, folks, because the velocity and the acceleration are in opposite directions, that means then they have opposite signs. This is negative here, and the velocity here is positive. We know then, what can we conclude? The object, the ball, is slowing down. Okay. Now, for some of us, we're going to take a look at this and say, well, wait a second. We have to push the ball up initially. We have to push the ball up first with the force initially, which is true. In order for the object, for the ball to roll up the hill, roll up the step, we have to push it first, and therefore the acceleration will be up. However, this problem is dealing with an object, the ball, that already has a velocity. That means then that what you have to think about then is that we've pushed the ball up, and then we let it go. At the point that we let it go here, it has this velocity. So there is no more force acting in the upward direction. There's only a force acting down. Okay? And what is that force? Hopefully you recognize then that the force is going to be the force of gravity, but it's going to be the x component of gravity. This part here, folks, you will learn when you get into physics, but it's that force that's pulling the ball back downwards. Even as the ball is moving up the ramp, their force is acting down, and the acceleration thus is also acting downward. Okay? All right. So there's acceleration. Again, the force part here, folks, don't worry about it so much. The force part here, that will come later when you go on in physics. But hopefully you're able to solve for this problem here. Okay. All right. So what I would like you to do here is take a couple of minutes to work out number 5 here, okay? And then what I'll do is I'll work it out for you, and then we'll finish up with this problem here, and then we'll continue our discussion of acceleration when we get back from break. So take a couple of minutes here to work out this problem, and then I'll work it out for you. You write down your answer, and then you submit it at the end of the video here, and then you'll be done for the day. Okay, so let's go ahead, take about a couple of minutes to work out this problem right here. Okay. Okay, let's go ahead then. Let's work out this problem, and I'm going to use the picture. So I'm going to draw the picture here to help us. Okay, so working out this problem here, we're going to draw the picture. So there is our object. Okay, our object is the hockey player, mass M. Moving along the horizontal here, we're going to call this the origin at 0 meters. Okay, he moves in a positive direction. Okay, so we'll talk about that. We were told then that he's moving initially, so that's the initial velocity. And so this, the right-hand side is the positive side of the motion. Left-hand side is the negative. So he's moving in the positive direction. Okay? And again, this is arbitrary. You decide what's positive, what's negative, but he's moving at a rate of 1.25 meters per second. Okay? We are told that at some point, because he hits a rough patch of ice, at some point, we'll write this here. So he moves, okay, and at some point, he ends up stopping. So V final here is going to be 0 meters per second. He stops. Okay? And so we're told then that again, we don't know how far he moved, but we know the total time interval in which he moved, and that's going to be 5 seconds. Okay, so we have a 5-second time interval as well, okay, here in this case. Okay, and we're asked to find the acceleration. Okay, all right, so the acceleration then is going to be the change in velocity over the change in time, which is, and I'll just extend it over here, V final minus V initial. And I'm just going to call this change in time interval, the time interval there as T. So plugging in what we know, V final is going to be 0 meters per second. V initial is 1.25 meters per second. Okay? And the time interval here is 5 seconds. And so our final answer then, if we plug that in, is going to be negative 0.25 meters per second squared. Okay, so that's our acceleration. That's the answer right there, which means then the acceleration is in the opposite direction. The acceleration is negative here. The velocity here is positive. The acceleration is in the opposite direction, which means then since A and V are in opposite directions, that means they have different signs. Okay. Because of that, object slows down. Okay. So that's how the signs here will help us try to figure out what's happening with this particular object as it's moving. Okay. All right, so very good, folks. I hope you folks have a good break. I will see you back here after your break. And like I said, I'll be here after school today. If you have any questions, stop on by and get your questions answered. And if not, then I will see you when you get back from break. Okay, have a good break, folks.